Welcome back, students. Yesterday we have done capacitors and dielectrics. Okay, the various aspects of dielectrics we have seen yesterday, and I ended the session with one work for you, one problem for you. That is, when a dielectric material of varying dielectric constant is placed between the plates of a capacitor, then what is the final equivalent capacitance? That was a question. I hope some of you tried it and got the answer also. Anyway, I will explain that. Let me start with that derivation and that concept. Let me remind you yesterday what we did little bit and then proceed further. Okay. So this is the last topic I dealt. That is, when a capacitor is there and when it is filled with dielectric of varying dielectric constant. So capacitor is filled with varying dielectric constant yesterday we did across the length of the conductor, across the length of the capacitor, across the length of the capacitor. That means we assumed like this, the capacitor plates and a dielectric material is placed between them. The dielectric constant is given by Ax plus B. This is we assumed actually. You can take, there may be other function also possible. For example, I have taken K equal to Ax plus B. That means this is the length of the capacitor. At this corner at x equals 0, it is having some B. As you proceed to the right, x equal, you have to substitute L. Across the length, all along the length, dielectric constant is varying. Then how to find the dielectric constant? Yesterday I explained this one. And today let us get into the second model here. That means the dielectric constant is varying not across the length but across the width. That means across the distance between the plates. That means D. That means it is changing like this. So yesterday it was changing like this. Now today let us discuss that is changing in this manner. Now the second case, dielectric constant is varying across the width, you can say the distance, across the distance between the plates, width of the plates or distance between the plates, you can say. So this is, let us discuss today. Okay. Now the diagram looks like this. So this is the capacitor with the positive charge in the upper plate and equal negative charge in the lower plate, and area of cross section of each plate is, area of cross section of each plate is A. Okay. And D is the distance between the plates. D is the distance between the plates, this one. Now this whole region is filled with a dielectric material. This is filled with a dielectric material whose dielectric constant is, let dielectric constant is varying downwards, you can say downwards across the width according to the relation. We can take any function here. As an example, I am taking this Ax plus B. That means x equal to what? The 0. X equal 0 here, and x, the maximum value of x is what here? You can say D. Okay. So that you try to understand it. Okay. This is how the dielectric constant is varying. Now, in order to calculate the capacitance of this arrangement, that means capacitor with this sort of dielectric material, what we do is we divide this into elemental sections. Yesterday, if you remember, the elemental sections were assumed like this. So this was the elemental section of the capacitor assumed like this. Okay. Now let us assume the elemental section of the capacitor like this. and the width of this one, the width of this element is something dx. What is the area of this one here? That is actually into the board throughout the plates. That means the equal area it is occupying, but the thickness is only what dx. And not only this element, there are various elements are there. That means we are dividing into various such elements. We are considering only one such element. Now you can imagine like this, having many capacitors in this manner. All elemental sections are connected end to end like this. This is end to end connection, we can say. End to end connection is always said to be is a series connection. End to end connection is nothing but series connection. And let us decide the capacitance of this and then integrate from this end to this end. So once you divide this into small sections, the capacitance of elemental section that I assumed there, and let us suppose DC is equal to, what you can write is K epsilon naught A by the width is nothing but dx here. Area is same, K the dielectric constant at that place for this particular one, and that is given as what? Ax plus b. What is x here? This is at a distance x from the upper plate. Okay, the distance between the plates is dx. Now the distance is x from the upper plate. So this is the capacitance of the elemental section. Now this is a series arrangement of many such sections. That means if you add all the capacitance of all these sections, you will get the net capacitance. That means for a series combination, as we discussed yesterday, the equivalent capacitance is nothing but 1 by dc integration. That means addition of, integration means nothing but addition of all such elements, addition of all such elemental sections. Yesterday we understood if two capacitors are in series, then the net capacitance is 1 by C equivalent to 1 by C1 plus C2, 1 plus 1 by C2, right? This is just like that. Instead of addition, I wrote integration because there are so many elements are there. So integration is nothing but addition of small sections. Now DC already we have this one, right? So let me substitute the DC value. 1 by C equivalent is integration of 1 by DC. 1 by DC nothing but K epsilon naught A by dx. Dx goes up, right? Dx goes up. Now what is the value of K in the give? That is given already. We assumed that one. So that can be written as dx by epsilon naught A. Let me keep aside, and K value let me take Ax plus B. Epsilon naught A is constant. You can take out of the integration, and integration should be done from where to where? It should be done from the upper plate to the lower plate. That means from 0 to the complete distance towards D. So therefore we have to do 0 to D straight away, right? And now here integration techniques comes into play. So 1 by epsilon naught A I am taking out of the integration. So dx by Ax plus B, this is the function here 0 to D. And let me remind you, one integration of 1 by x dx is nothing but ln x or simply log x. Okay, so suppose if I write Ax here, Ax dx, this is nothing but 1 by A ln x. If I write something 1 by Ax plus B here, that is also the coefficient of x comes here 1 by A ln of Ax plus B. So they are the mathematical formulas. Anyway, you need to understand, you need to know them before coming here to this evaluation. So integration of this one, let me write straight away ln Ax plus B, limits are what? 0 to D. You can also write instead of ln, you can write log base E also you can write. Both are same, log base E, or sometimes I write ln, ln I said, both are same. Now, so let me finish this one. 1 by epsilon naught A, put the upper limit in the place of x here, ln, and sorry, 1 by A comes here. This is just now I told here 1 by A comes here, this is 1 by A. Let me write that A is anyway constant, keep outside the the substitution of the limits. So, this is AD plus B, in the place of x I substituted D, minus ln, in the place of x substitute 0, you will get B. Okay. Now, generally what mistake we do is, we don't do this one. Instead of that, what we do is, integration of DC we do directly. We directly add DC. That is a mistake there. You have to integrate in the reciprocal, because in the series we have the reciprocal addition is there. That's where you generally we commit a mistake, and we don't know how to evaluate that later on. So, that is that mistake we should not do. Okay. Now, log m minus log n is nothing but log of m by n. So, AD plus B by B. So, this is 1 by C equivalent. Therefore, the equivalent capacitance now reciprocal of this, then what we will get is, this goes up A epsilon A by logarithm of always ln AD plus B by B. So, this is the final formula. See, this is not to be remembered. This is a problem actually we are discussing. This is a sample example, I mean sample problem here. Example problem, I would like to explain you how to find the capacitance in different situations. This is not a formula to be remembered. Don't remember, but the method you try to understand. So, the two methods I explained, one is the dielectric constant is varying across the length, and the dielectric constant is varying across the width. So, these methods know you have to understand, and then you can implement those methods to unknown questions there, which will be given in the entrance examinations. So, take note down, take a note of all this derivation, and then let us move to the next concept. Okay. Students, let us discuss one more this is a very important topic, even every entrance examination point of view, whether it is NEET or whatever MSET mains. So, this topic is very important. Okay. Effect of insertion of dielectric slab in a capacitor. That means we are inserting a dielectric slab or a material into the region between the plates. There are two possibilities here. When the battery is still connected, there are the two cases let us discuss. Still connected. Second case is when the battery is disconnected. That means we are inserting the dielectric slab, and then we are disconnecting the battery. We are inserting the dielectric slab, and the battery is continuously be connected, still connected, right? There are two cases when the battery is disconnected. So, these two cases let us discuss, right? Then what will happen to the various parameters to the capacitor, let us discuss now. So, this is a situation where let us imagine this is a capacitor, a parallel plate capacitor is taken and connected to a battery, and yesterday I told you in the steady state, that means when the capacitor is charged fully, when you connect the battery will take the charges on one plate and place on the other. One plate will become positively charged, and since all the charge is placed on the other plate, that becomes what? Negatively charged. So, equal and opposite charges are formed on the two plates. This is you know already. So, when when the capacitor gets charged, you know there is a potential difference established between the two plates. Immediately there is an electric field created between the two plates. So, let us suppose Q is the maximum charge, the charge in the steady state, you can say the charge in the plates, and V is the potential difference between the plates. That is nothing but where from you got this potential difference. Actually, whatever the potential differences between the plates is generated or created by the external battery. The potential difference between the plates is equal to in the steady state, equal to the potential difference or EMF of the battery, you can say. Okay, potential difference between the plates is V, and E is electric field intensity between the plates. Intensity between the plates. And you know the value of this one equal to sigma by epsilon naught, and sigma is nothing but charge density, that is charge per area, Q by A epsilon naught. This value already you know, and E equal to, you can also write V by D, where D is the distance between the plates. Where D is the distance between the plates is D, and A is the area of the plates. You already know that, isn't it? Now, there is one more aspect here. Capacitance of this capacitor is nothing but whenever there is no medium is there. Whenever there is no medium is there, just free space is there, the capacitance is nothing but A epsilon naught by D. And when we fill the slab, we already know, we discussed yesterday, when the dielectric slab is, when the dielectric material of dielectric constant K is inserted between the plates, always remember, always the capacitance increases, always capacitance increases K times. That means you are completely filling the space, not partially, right? In that case, the capacitance increases K times. Therefore, you can say C dash equal to what? K into C, that is nothing but K A epsilon naught by D. All the parameters you must know. And not only this, the energy stored also we discussed, the energy stored between the plates. The energy stored between the plates is given by U, generally we represent half CV square. We derived this equation in the one of the previous sessions, and this can be also written as Q square by 2C. This can be also written as 1 by 2 QV. See, Q is nothing but CV, you will get CV square. If you substitute Q equals CV, you will get back again half CV square. All the formulas are very important to remember, right? So, this is the energy stored between the plates. This is a background you need to have before discuss the two cases now. Now, let us discuss the two cases. The first one is when the battery is still connected. That means now you are placing, now already this is charged. Already that is charged. That means the potential difference is something V here. Now the dielectric slab is inserted in the region between the plates. Now we are bringing into the region between the plates. Then what will happen to all these parameters? That is important. That is the subject matter to be discussed now. What will happen to charge? What will happen to V? What will happen to E? And what happens to C? The very first thing is, you have to understand, very first point is capacitance increases K times. Always I said increases K times. So, this is the first point, capacitance is Kc, that is nothing but K epsilon naught by D. Yesterday clearly I told you the electric field decreases when you place a dielectric slab. And one more thing is, since the battery is connected, the potential whatever the battery can give to this one in the region between the plates, that remains same, because the batteries can supply the same potential to the battery capacitor plates, that remains same. Let me write that. Since the battery is connected, battery is still connected, the potential difference between the plates do not change. Between the plates remains constant, because the battery can offer some potential difference, a fixed potential difference in the plates, therefore that remains constant. The second point, this is the first point. The second point is V is remaining same, V is same, remaining constant, that do not change. When V do not change, since E equal to what you can say, V by D, equal to what? V by D, the basic formula between E and V. Since V is constant and V is constant, therefore E do not change, E remains constant. Therefore E is constant again, E is constant, right? But since the dielectric slab is placed here, the capacitance increase. Since the capacitance increases, the battery can place more charges onto the capacitor plates. Let me write that also. Since capacitance increases, battery can place more charge. I am giving the regions also here, more charge on the plates. Therefore, the new charge is the charge q dash, let us suppose k times q. That means the charge do not remain same. It's q dash equal to what? kq. And the last one, so we discuss everything. Q we discuss, V we discuss, E we discuss, capacitance we discuss. Now let us discuss the energy stored. The last point is what will happen to the energy stored? Which formula you have to use to understand this? Energy stored, let us suppose U dash. Which formula let us use? If you can use any one of them, but always remember you have to select a formula in which there are two variables everywhere and one of them should be constant. Suppose if you use this formula, that is better. Because why? Because V is constant and C is changed. Therefore, let us use this formula instead of the other formulas. Okay, let us use this one. Now, you can use also this one because Q change and V do not change. Okay, here both are changed, but better to use either this or that. Let us make use of the first one, half C dash V square, and you can say K into half CV square. Therefore, K into U. Therefore, the energy increase what? K times. The energy increase how many times? K times. So, I can write the last one U dash equal to K into U. So, this is what happens. All these points logically remember. Logically you have to remember, you cannot memorize them because see, the first point is capacitance always increases when a dielectric slab is placed. You start with that, you start with this and then see the situation. What is the situation here? The battery is still connected. When the battery is still connected, it offers the same potential difference. Actually, when you place a dielectric slab, potential decreases actually, but that is compensated by what? The battery again. Yesterday we learned whenever you place a dielectric material, electric field intensity decreases, potential decreases, capacitance increases. That's okay. Here actually the electric field decreases and the potential difference also decreases actually, but still since the battery is still connected, it will compensate that loss. That means it will again feels the same potential. Therefore, potential is constant. Therefore, since potential is constant, logically remember the relation between E and V is constant. And since the capacitance increases, follow this logic again. That means you can place more charges on the capacitor plates. Therefore, the charge is multiplied with K. And the energy you can understand from this formula. So, this is the first case where the battery is still connected. And the second case, let us discuss. First of all, it is already charged and now the battery is removed. That case we discuss all the parameters again we should check in. Okay. So, let me rub that part of the board and I will explain all of them. Just stay tuned. Okay. Discuss the second case here. The second case is dielectric slab is inserted and the battery is disconnected. Now, let me explain you again. So, the capacitor is completely charged by using a battery. That means it is already charged. Now, we disconnect this. After it gets charged, we disconnect this and let us insert a dielectric slab. Let us bring a dielectric slab into the region between the two plates. Then let us discuss all the parameters again. The very first point, as I said, capacitance increases K times. Capacitance increases K times. So, therefore, C dash equal to what? K into C. This is anyway, in the two cases, this is the only common point. Now, yesterday we discussed whenever a dielectric slab is placed, between the plates, always, that means in here battery is not there, electric field intensity decreases If you remember the yesterday's discussion, the one of the previous discussion, induced charges will appear here. There is induced electric field generated in the region between the inside the dielectric, whose direction is opposite to the external field direction. Therefore, electric field intensity decreases, and E dash equal to E by K, decreases by K times. I am not telling again all the reasons here why it decreases and all that. In the one of the previous classes, I clearly explained why it decreases and how much it decreases. I clearly explained in the one of the previous classes. Just consult that lecture if you could not follow this. Okay. Now, since E equal to V by D, because D is not changing here, since E decreases since E decreases, V also decreases by K times. So therefore, V dash equal to what? V by K. See, in the previous case, the battery actually the potential will decrease, but the battery compensated that loss, I said. But now there is no battery, there is no compensation takes place. So V dash equal to what? V by K. And one more point is, since there is no further charging, because the battery is not there, further charging, charge remains same. Therefore, Q dash equal to what you can say? Q dash equal to Q. And the last one to be discussed is energy stored. Now you can think which formula is better to use here. Energy stored between the plates. Which formula to be used? Now you can check. Let us make use of this formula because charge is same and the potential got decreased by K. So therefore, new energy is, let us use this formula, half Q dash V dash, but Q dash is Q, V dash is V by K. So 1 by K, half QV, that is nothing but U by K. Therefore, you can say energy decreased by, in the previous one, energy got increased, energy stored decreased by K times. So these two topics are important to be understood, and anyway I think you understood it very clearly. If not, again play it back and then see, then there is every chance that you will understand better. But if you miss any previous classes, it is very hard to understand. You must come in a sequential manner, then only you can understand. Okay. Now take a note of this and let us move to the next one. Students, let us take up an isolated topic here, that is a Wheatstone's bridge. I think you got this one in your 10th class with what you can say resistors, right? But here with capacitors, let us discuss. Anyway, we will come across the Wheatstone's bridge. This is an isolated topic, okay? So this is one of the examples where why I want to tell you is, you must know how to analyze a capacitive circuit, okay? Because in the examinations, the circuits comprising of the different capacitors are given, and you have to find the charges on the various capacitors, the potential difference on between the plates of the various capacitors, and the equivalent capacitance you have to find. These things are generally asked in various capacitive circuits. And one of the capacitive circuit, that means one of the circuit which is consisting of several capacitors, is called as Wheatstone's bridge. So why I am telling this is because this is useful in problem solving, okay? And anyway we must learn this one. And similar Wheatstone bridge with the resistors we will get in current electricity also later on, right? But for time being, let us discuss this Wheatstone bridge. And one more thing is, yesterday while telling the capacitive circuits, the combination of circuits, capacitors, how you can combine the capacitors? Either in series, that means capacitors are connected end to end, that means series connection, or capacitors can be connected in a parallel combination, or a mixed combination, means series and then parallel. And some circuits are there which no more called as series connections or cannot be also called as a parallel combinations. So in such a complicated circuits, I told you one important method to be used is nodal analysis. I told you little bit I introduced in the previous classes, the nodal analysis or the junction analysis. And while discussing this one, because Wheatstone bridge having capacitors is not a series combination, is not a parallel combination. So in such a case, the nodal analysis will be very useful, and let us see how we can apply the nodal analysis here and what is the circuit which is called as Wheatstone bridge. Now it's very simple one. See here, it is this is one capacitor C1 and this is another capacitor C2, this is C2 and this is C3 and this is C4, and there is one more capacitor here, that is C5, connected like this, and these terminals are connected to a battery. See, if there was no capacitor here, these two are in series and these two are in series, and this branch parallel to this branch, and these are not parallel because of this, these two are not series because of this. So this is not a series combination, not a parallel combination as well. Now what battery will does is here, the battery will take some charges from C1 and C2 and will be placing on the plates of C3 and C4. So here it will take a charge Q1 from this plate, and here it will take a charge Q2, and this charge will flow across the battery terminals, and this charge is placed on C3 and C4, and let us suppose this is minus Q3 and this is minus Q4. And clearly Q1 plus Q2 is equal to Q3 plus Q4. What are the charges taken from these two plates will be arranged on C3 and C4. Therefore, how much charge is flowing across the battery? Therefore, the charge Q1 plus Q2 is flowing across the battery terminals. Across the battery terminals. So the equivalent capacitance what you can write is delta Q. You can say the total charge flowing through the battery terminals by V, but delta Q is nothing but Q1 plus Q2 by V. That means by some method, if you can calculate Q1 and Q2, then you can calculate the C equivalent. And of course, I said Q1 plus Q2 is nothing but equal to Q3 plus Q4. So therefore, even if you find Q3 plus Q4, then also you can find the equivalent capacitance. This is one basic idea. Okay. Now, since the capacitors are having equal and opposite charges, here you will get minus Q1, here you will get plus Q3, here you will get plus Q4, and here you will get minus Q2. And since the charges are supplied to the various plates here, this capacitor, there is some potential difference is generated at this junction, let us suppose M, and this junction, let us suppose N. So these are also called nodes or junctions. So because of the supply of charges, some potential difference is developed here, and here also some potential is developed here. So let us suppose the potential here is X and potential here is Y. And since the battery is generated here, the potential at this point is V. The positive terminal, you can take V also here, or you can take V also here, and since negative terminal is connected here, there is a potential developed 0. So these are called junctions or the nodes. Here you can apply the point here is, there are various questions comes here. The various questions is, what are the questions can be asked? Generally you can think of the questions, what is the charge on Q1 in terms of C1 and V? What is the charge in the capacitor C2 in terms of C2 and V? And Q3 and Q4 in terms of the known capacitances and the potential difference of the battery? And what is the charge in the C5? And what is the potential difference? What is the potential difference between M and N? What is the potential difference between this capacitor? What is the potential difference between this capacitor? So these are the various questions we need to answer, right? We need to. These are the questions now. How we can answer these questions is by using nodal analysis. Let me write here, by using nodal analysis. This is very important tool in understanding this complicated circuits, right? We can find the charges on various capacitors and also the potential difference across capacitors, right? Because I want to know what is the potential difference across C5, that also you can find, and we can also find out the equivalent capacitance of the entire circuit. So these are the questions you can answer, right, by using nodal analysis. Let me write the nodal equations for this circuit. That means the potential is X here, the potential is Y here, the potential is V. That means the potential here is V, and here also you can say V. Okay. So let us apply the nodal equation. Let us write the nodal equation for junction M, junction R, you can say node M. Okay. That means you concentrate here, If X is greater than Y, this is positive polarity plus Q phi. If X is less than Y, it will be minus Q phi, and this is plus Q phi, depending on whether which is at higher potential. And now if you write the equation for the M, then if you look here, actually this V is higher than this X here, but the algebraic sum of all the charges here, is 0. This one. That means minus Q1 plus Q3 plus Q phi is 0. Or if you write a nodal equation for here, this minus Q phi minus Q2 plus Q4 is also 0. Because the charge is nothing but C into V, right? So therefore you can write minus Q1 plus Q3 plus Q phi is 0, right? Minus Q1 can be written as C1 into V minus X. C1 into V minus X, but minus is there. What you can write now? C1 into X minus V. I am writing the minus of that. Plus Q3 is what? Q3 you can write C3 into, what is the potential difference here? X, and what is here? 0. X minus 0. What is Q phi now? Q phi you can write X minus Y, that is C phi into this is one equation. Now writing the nodal equation for junction or the node N, what you write is minus Q phi plus, what you can say is minus Q2. Let me write minus Q2 minus Q phi plus Q4 is 0. Okay. And here we assume this is at higher potential than this. So therefore, what you can write is this is C2 into what you can write is Y minus V plus C phi into Y minus X. Because this minus Q phi is there, Y minus X, you are looking from this to there. And here what you can write is C4 into Y minus 0 is equal to 0. So this is the second equation. Now here comes the Wheatstone bridge. The condition for Wheatstone bridge is, from these two equations, one important condition is, let us apply some condition. Let us make one condition, that is if X equal to Y. So this is the condition we are making. That means if the potential of X is equal to Y, that means immediately the potential difference between the junctions is 0. That means the capacitor C phi is no more charged. The capacitor C phi is charged only when there is a potential difference between X and Y. Otherwise it cannot be charged. So what condition we are making here? X equal to Y. That means the capacitor phi is no more charged. So let us see what will happen to these equations 1 and 2 now if X equal to Y. So let me write them. C1 into X minus V, I am not changing this, plus C3 into X. X equal to Y is 0, therefore 0. Or you can write C1 into V minus x equal to, you can write C3x. Let me write this is equation 3. See, x minus v I change to v minus x there, taking to the other side. And this equation how it changes is, this equation how will changes C2 into, because y equal x, I can write x minus v plus C5. This is anyway 0 plus C4, I can write y equal x, therefore I can write 0 again. So taking the right side, I can write C2 into v minus x is equal to C4x. This is equation 4. So these two equations are very important here. Now what I do is I divide 3 by 4. And then what you will get is C1 into v minus x by C2 into v minus x is equal to C3x by C4x. X cancel, v minus, so C1 by C2 is equal to C3 by C4. So if you come back to this circuit here, C1 by C2 will be equal to what? C3 by C4. So this condition is called Wheatstone bridge condition. So this condition is called Wheatstone bridge condition. And this will happen, only if x equal to y. That is very important to remember. Under that condition only you can write this equation, and reverse is also true. That is also very important. Let me write also the reverse is also true. Reverse means what? Reverse is also true means if C1 by C2 is equal to C3 by C4, then x equal to y. That means the charge in the capacitor phi, the charge in the capacitor C phi is 0. So these are the end results, and our job becomes so simple by using the nodal analysis here or the junction analysis. And once C phi is 0, you can remove C phi now from the circuit. That means C phi is ineffective now because there is no charge on the C phi. Let me write that also here, just done here. So therefore let me write that final points here. Since the charge on charge on C phi is 0, C phi is ineffective in the circuit, is ineffective and can be removed, So in that case the circuit looks so simple now. In those conditions circuit looks so simple. So that will be like this. This is C1, C2, C3, C4. C phi is not, even it is present, it can be ignored. Now in this case the equivalent capacitance is simply, equivalent capacitance is nothing but C equivalent is C1, C3 are in series and in parallel to the what? C2, C4 series combination. C2, C4 series, C1, C3 series, and then parallel here, and this can be written as C1, C3 by C1 plus C3, and parallel means plus C2, C4 by C2 plus C4, and this is the equivalent capacitance when under Wheatstone bridge condition. So this is the equivalent capacitance. If this condition is not met, that means if x equal to not y, not equal to y, then also we can find out the potential difference between x and y, the potential difference. All these questions can be answered by using this analysis. If possible, in the next class I will take an example with the values here, and let us find everything, whatever the questions I ask here. In the beginning of the next session, I will give an example so that you will appreciate the nodal analysis here. then we will move to the some alternate formulation. See, the Whitson bridge that has given here is generally framed in different ways, and alternate appearance of the Whitson bridge also in the next class I will explain you. Okay. So, I hope you understood this. I will meet again in the next session. Till then, goodbye.